Hey guys, how's it going? I'm about partway through grading the product rule, quotient rule, chain rule test. It's looking like we might need a little bit of re-engagement lesson of some kind on that. Some are outstanding, but definitely some important concepts missed. So on Monday we'll take a look at that, and I got to think about that for a little bit this weekend as I finish grading those tests. So this video, we may not fully work on it in class, practice it in class until Wednesday, but have it done for Monday anyways. So just in case, as I continue to grade the test, they start looking a little bit better. Okay, so we're going to talk a little bit about implicit differentiation here. It kind of sounds, it sounds difficult, but hopefully you'll find it to be pretty strong, pretty good for you. So first off, we need to talk about what the word implicit means. Differentiation is another word for doing a derivative. But the word implicit, right, comes from implied. So it's a little bit, it's the opposite of explicit. So let's just take a look at the difference between explicit versus implicit in terms of the variable y. So if we have an explicit function, that means it's solved for y. So something like y equals sine x, or y equals 3x squared plus 5x minus 2, or y equals the natural log of x cubed minus 5. All of those formulas, y is explicitly solved for, meaning that there's we have it written as y equals, and then some kind of function in terms of x. Implicit curves, y is not explicitly solved for. And it could be as simple as just rearranging an explicit, but usually it's a little bit more difficult than that. Here are some examples of implicit functions. Okay, so you can see when we're talking about implicit, I'm going to resist the urge to use the word function because oftentimes these things aren't functions. They're relations or curves. They could fail a vertical line test. But if you notice, y isn't explicitly solved for. It doesn't say y equals. Sometimes there are y squared. Sometimes there are multiple y's. We have y squareds, y's. We might have sine y, cos y, things like that. Yeah. When we do implicit derivatives, okay, I have a series of steps that I want you to write down and how to solve this. So here are some things to keep in mind with implicit differentiation. Okay, so number one, we have to derive all terms in the equation. So we have to do the derivative of all the different terms in the equation. This includes x's, y's, and constants, and anything else. So we have to derive all of the stuff in the equation. Our second thing to remember is derive x values normally. So anytime you come across an x, do the derivative as you normally would. Y's are where we have a little bit of a difference. When you come to a y term, do the derivative as normal, and then multiply by dy dx. Think of it like a chain rule, and we're multiplying by the inner function y, the derivative of the inner function y, with dy dx. Okay. For example, if you see x squared, the derivative would be 2x. If you see y squared, the derivative would be 2y dy dx. We'd have to multiply by dy dx. That's the big difference. Number 4, all derivative rules still apply. So that would be power rule, product rule, quotient, and chain. So if we ever have a product of two functions, we still have to do the product rule, which is derivative of the first times the second plus the first times the derivative of the second. If we see a quotient rule, we have to do that. If we see a chain rule, we have to do that. So all our rules that we learned in the last unit still apply. Okay. The last thing you need to do is isolate dy dx and simplify. So those are the rules for doing implicit differentiation. What I'm going to do is I'm going to do several examples of this. Now again, if you're shaky on the product rule and the quotient rule and the chain rule, this is also going to be shaky. Okay, which is why Monday I need to make sure that we are better at those rules to make sure we follow them correctly. Okay, so those rules are still going to apply. So we need to master Unit 2 before this. So let's take a look at some examples of what I'm talking about. The first curve we're going to look at is x squared plus y squared equals 25. Now, if you think about this, where have you seen an equation like this before? Well, if you think about this, right, and think back to geometry, we know that that's the equation for a circle centered at 0, 0 with a radius of 5. Now, you don't have to know that to solve the problem here, but it's helpful to think about that, right? This graph would look like this. So we can see right away that this is not a function because, you know, one x value, right? One x value can give two separate y values, right? We can see this thing fails the vertical line test. It's not a function, okay? But we can still come up with a derivative dy dx. So our goal here is to find dy dx. So that's what we're going to do here. And what we can do then is with that dy dx, we could plug in any point x, y that is on that circle, and we can figure out the slope of the tangent line at that point. For example, a point that would be on this circle is the point 4, 3. The point 4, 3 satisfies this equation because 4 squared is 16, 3 squared is 9, 16 plus 9 equals 25. So what our goal here is we want to find dy dx so we could evaluate dy dx at that point 4, 3 and see what the slope of that tangent line is. Now just looking at, looking at this graph here, we can tell a slope of a tangent line here should have a negative slope. I'll use a different color for the tangent line. All right, so if we plug in the 0.43 into our derivative, we will get a negative slope. Okay, I'm also going to talk about the notation we use for plugging in a point into dy dx. All right, we're used to seeing that with f prime, right? F prime of 3, right, means evaluate the derivative at 3. But how do we use that notation for dy dx? We'll take a look at that too. But first, we need to get an equation for dy dx. So, following our steps, we need to derive every term in this equation. So, x squared, y squared, and 25. We have to do the derivative of all three of those things. We're going to derive x normally. When we derive y, we're going to multiply by dy dx. And then we have to follow any rules. Now, right away, I don't see any rules other than the power rule, okay, because I don't see a function times a function. We'll look at some of those, or I don't see a function divided by a function. We'll take a look at a couple of those in here. So this one should be pretty straightforward, and then I'm going to isolate dy dx. So here's what I'm going to do. I'm going to go through and do the derivative of each term, and I'm going to work left to right. The derivative of x squared here is simply 2x. That's all I have to put because I derive x normally. Then I have the plus here. Now I have to do the derivative of y squared. Well, the derivative of y squared here is going to be 2y, but I need to multiply by dy dx. I can just write the dy dx next to the 2y, and it's implied that they are multiplied together. Okay, but I have to remember that every time I do the derivative of y, I need to multiply by dy dx. Okay, and don't stop there because we haven't derived all the terms yet. I now have to do the derivative of 25. Well, the derivative of a constant is always equal to 0, so I'm going to have equals 0 on the right side. Okay. But I followed all my rules. The only rules here were power rules, right? No product, no quotient, no chain. So now the next thing I want to do is isolate dy dx. So I'm going to isolate dy dx. I want to get it alone. So I have to first get that 2x out of there. So I'm going to do that through subtraction. And I get 2y dy dx equals negative 2x. Then I'm going to divide by 2y. And I get dy dx equals negative 2x over 2y. Okay. The next thing I want to do is take a look. Now that I've isolated dy dx, I have it by itself. I'm going to see if there's anything that reduces. Well, I see a 2 in the top and a 2 in the bottom, right? And there's only one term in both the top and the bottom, so I can divide those 2's out, and I can get dy dx equals negative x over 1. That would be my final answer here. Now, if I wanted to evaluate the derivative at a point, okay, here's the notation, right? So evaluate dy dx at the point 4, 3. The notation for that would look like this. So what we use is dy dx and then a big vertical line there. And then down low there, I'm going to put the 0.43. That means I'm plugging 4 in for x and 3 in for y into my function dy dx, which is negative x over y. So what I get is negative x. Well, this is my x, this is my y. I've got negative 4 over 3. So what I get is the slope of this tangent line here. This slope is negative 4/3. Okay. Let's take a look at a couple more examples. Sometimes these things we can recognize the shapes of. Sometimes what the curve looks like. Sometimes we can't. Okay, here's another example. Okay, so I have an equation here that says 4x squared plus 3y minus 4y squared equals 18. Again, my goal here is to find dy dx. So taking a look here, I just need to derive every term. I'm going to do x's normally. I'm going to do, anytime I do the derivative of a y, I'm going to multiply by dy dx. Again, the only rule that's going to apply here is the power rule. Then I'm going to isolate dy dx and simplify if I can. Okay, so let's go through and do the derivative of each term. I'm going to start with this 4x squared. The derivative of 4x squared is 8x. I do not need a dy dx on that derivative because I'm doing the derivative of x. But the next one, the derivative of 3y, I will need to multiply by dy dx. Now the derivative of 3y, right, is just going to be 3, but I can't forget about multiplying my dy dx. So the derivative of 3y is 3, but I need to multiply that 3 by dy dx. So it'll look like this. So the y term itself goes away, but the derivative of 3y is still 3, so the 3 needs to be there, also multiplied by dy dx. The next derivative here is going to be negative 8y. Again, I'm doing the derivative with respect to y, so I need to multiply by dy dx. And that equals the derivative of 18, which is 0, because it's a constant. Now my goal here, again, is to get dy dx by itself. But the problem you may see is, hold on, we got two dy dx's showing up here. Well, that's okay. We can easily deal with that. The first thing I'm going to do is keep the dy dx's on the same side of the equal sign. Now I can do that by moving the 8x to the other side, or I can move both the 3 dy dx and the minus 8y dy dx to the other side. I'm going to keep the 3 dy dx and the minus 8y dy dx on the left side, and I'm going to subtract that 8x over. And I'll get 3 dy dx minus 8y dy dx equals negative 8x. Now, to get my dy dx to be isolated, the way I'm going to do that is by factoring dy dx out of both terms, right? I see a dy dx show up in both terms. I'm going to factor that out. And what that's going to look like is this. So I simply factored, right? Doesn't matter how many dy dx's you have, just get them all together and then factor it out. Now, after I factor out that dy dx, I'm going to divide both sides by 3 minus 8y. And I'll get dy dx equals negative 8x over 3 minus 8y. Now I'm going to take a look and see if I can simplify anything. Now, I saw some simplifying that was not very good on the, well, I've been grading the tests here. Okay, the question for you is, can I cancel out those 8s? I see an 8 in the top and an 8 in the bottom. Well, the answer is I most definitely cannot cancel those 8s because 8 and 8 are both divisible by 8, but that 3 is not. So I need to leave it like this. Sometimes what you'll see, this is another one that's can be tough on multiple choice, because sometimes they just solve it a little bit differently than we did. One thing that they might do, again, on a homework assignment, I'd want you to box this. But for multiple choice, we need to be able to make our answer look like their answer. One thing they do, sometimes it just comes out differently than mine look, is but you can make it look like it by dividing every term by negative 1. So another way that this could be written now, if I divide the top by negative 1, I'm going to get a positive 8x, or think of it as multiplying by negative 1. And if I multiply the bottom by negative 1, it's going to make the 3 negative and the 8y positive. This means exactly, these two things are the same. Okay. Now, there'd be no reason for you to make that change other than the fact that maybe it's on a multiple choice and 8x over 8y minus 3 is on there, but negative 8x over 3 minus 8y isn't on there. Right? So that's the only reason we'd want to make that change there. But just be aware. Basically, what's happening here is every term is switching signs. The negative 8x and the negative 8y are becoming positive, with the 3 becoming negative. As long as every single term switches signs, we can do that. Okay, let's take a look at a couple more here. Okay, so when we take a look at this equation here, we have 4x cubed plus 8xy plus 2y squared equals 10x. Now, the only thing that looks a little bit different is that 8xy. What you need to be able to do is you need to recognize that 8xy as a product of two functions, right? There's no time sign that's visible, but it's implied that this is 8x times y. So when we do that part of the derivative, we need to use a product rule there. And I'm going to think of the first term as 8x, and I'm going to think of the second term as y when I do my derivative of the first times the second, plus the first times the derivative of the second. Okay, so let's try this one, and maybe this will be our last one for this video. Okay, again, our goal is to find dy dx, so we're just going to derive each term. 4x cubed we do totally normally. We just do the power rule. 3 times 4 is 12, so we get 12x squared out of that first derivative. Okay, so we've done that derivative. Now I have to do the derivative of the product of 8x and y. So the product rule says I do the derivative of the first. Again, 8x is my first term. Y is my second. So the derivative of the first is 8. I do not need a dy dx because I did the derivative of x. So the derivative of the first times the second, y, plus the first, 8x, times the derivative of the second. Well, the derivative of y is 1, but it's 1 times dy dx. Now, I'm not going to write in that 1, but I do need to write in the dy dx. And now I've completed the product rule. Again, this derivative of the first times the second plus the first times the derivative of the second. Okay? But now I need to continue to do the derivative for the rest of the terms. The derivative of 2y squared would be 4y dy dx. Again, don't forget, anytime we do the derivative of y, we need to multiply by dy dx. Equals the derivative of 10x, which is 10. Okay. And again, I want to isolate dy dx, so I'm going to subtract away the 12x squared and the 8y. And I'm going to do that to both sides. I'm going to get 8x dy dx plus 4y dy dx equals 10 minus 12x squared minus 8y. Now I'm going to factor out my dy dx. And I got 8x plus 4y here. And then I'm going to divide, and I'll get dy dx equals 10 minus 12x squared minus 8y over 8x plus 4y. And again, I like to look to simplify, because on multiple choice, the answer will be simplified. Okay, here's the question. Can I cancel out any x's? Well, the answer is no, because this doesn't have an x. Neither does this. Neither does this. Can I cancel out any y's? Well, no, because these three all don't have y in them. But when I look at the coefficients here, 10, 12, 8, 8, 4, all of those numbers are divisible by 2. So I'm going to divide all the numbers by 2 in this equation, and I'll get a final solution of 5 minus 6x squared minus 4y over 4x plus 2y. Okay. So, a good little intro here to implicit differentiation. That's it for today. I certainly hope this video actually saves all the way through. So, fingers crossed. 2 chains. See you guys on Monday. Bye.